So with chapter 7, we're dealing with atomic spectra. We're talking about electromagnetic radiation. And so electromagnetic radiation has wave and particle properties. And so one of the things that we discuss in this chapter is the properties of a wave that involves frequency and wavelength. And so those two are related by the speed of the wave, and we'll see that in a second. And for electromagnetic radiation, they all travel at the same speed, which is the speed of light. So if we know, for example, what's given here is the frequency, which is in units of hertz, then we can determine the wavelength. And typically with wavelength, we're looking at one of two units they usually want wavelength in, typically nanometers, which is in this problem, or they may want it in angstroms as well. Those are the two common units that we use to calculate wavelength. So what we have to know is that the speed of a wave is equal to the wavelength, which is lambda, and the frequency, which is nu. And this C for electromagnetic radiation is always going to be 2.998 times 10 to the 8th meters per second. So all electromagnetic radiation travels at the speed of light, which is 2.998 10 to the 8th meters per second. And so if we want to solve for wavelength or frequency, we can rearrange this equation because C is a constant for electromagnetic radiation. And so we get lambda is equal to the speed divided by the frequency. And again, frequency and wavelength are inversely related to one another. So if you have a high frequency, you're going to have a low wavelength and vice versa. So then we just set it up. Make sure you use parentheses because if you don't, your calculator does it based on order of operations. And so it may give you some wild answer. If you got like 10 to the 22nd, most likely you didn't use the parentheses correctly. And then we get the lambda, which is in meters. We have to convert to nanometers. So again, 1 meter is 1 times 10 to the 9th nanometers. So we simply multiply 8 10 to the negative 7 by 10 to the 9th, and we get nanometers. So this is an 800 nanometer wave. So electromagnetic radiation, we talked about we talked about wave properties, which is wavelength and frequency, but also electromagnetic radiation has particle properties, which means it's consisting of photons. And if something is a particle, it has mass. If it has mass, it has momentum. And then we have the energy of a photon. So that's something we can calculate when given its wavelength or frequency. So if we know the wavelength a photon is traveling at, we can calculate the energy associated with it. And so here when we're looking for the energy of and this is just of a single photon, is this equation, we get E equals h nu. And so E, of course, is energy. H is what we refer to as Planck's constant, joules second. So that's about the fastest an energy can be transferred. It's 6.626 times 10 to the negative 34 joules every second. And then we have frequency. So what this tells you is that frequency is directly related to energy. If you have a high frequency wave, you're going to have a high energy associated with it. And from the last problem, we know that frequency is C over lambda. So what we can do is if we substitute C over lambda for nu in the energy equation, we get energy equals hc over lambda. So the wavelength is inversely related to the energy. So something with a long wavelength is going to have a small energy associated with it. So for example, radio waves, microwaves, TV waves, those are types of electromagnetic radiation with long wavelengths. They're not very energetic. That's why they don't really affect us. But if you look at something like X-rays, gamma rays, UV rays, these have very short wavelengths, have very high energy, and they're very energetic. So cosmic rays or gamma rays can really destroy, you know, biological objects like plants and stuff, and even humans. So now we need to first, when we're using the energy equation, since C is meters per second, we have to make sure lambda is in meters. So again, the wavelength given to us is in nanometers. So the first thing you should always do is convert it to meters. And so to do that, we know that 1 meter is 10 to the ninth nanometers. So 1 nanometer is 10 to the negative 9 meters. So we take 1 times 10 to the negative 9 times 1205, and we get the lambda in meters. Make sure you do this conversion, because to use this equation, lambda has to be in meters. So now we have lambda in meters. We can set it up and make sure you use parentheses. So what I would recommend doing first is 2.998 times 10 to the 8 times 6.626, 10 to the negative 34. Get your answer, then divide it by parentheses 1.205 e to the negative 6, close parentheses. Because if you don't use parentheses, you're going to get some kind of wild answer as a result. And so when you do this, you get, energy is about 1.6 times 10 to the negative 19 joules. Now again, this is the energy of 1 photon with a wavelength of 1205 nanometers. So here we have a little different problem. We have a beam of photons, has an energy of 987 kilojoules per mole. What is the wavelength in nanometers of a photon in this beam? So again, what we learned from previous problems, that's the energy of a photon is equal to hc over lambda. So if we know the energy of a photon, we can rearrange this equation to solve for wavelength of that photon with that particular energy, because h and c are constants. And so what we have to use here is Avogadro's number, because so far what we know is the energy per mole of photons. But we want to know the energy of 1 photon, because E equals hc over lambda is the equation to calculate the energy for 1 photon. Right now we have the energy of a mole of photons. So we need to use Avogadro's number to convert from a mole of photons to 1 photon. And so what we do is we divide by Avogadro's number, we get the energy per a photon. So now we get the energy per photon, but notice here that the energy is in kilojoules. But in our Planck's constant, energy is in joules. So before we can plug it into this equation, we need to convert energy from kilojoules to joules. And again, you can do this in different orders, but this is just the order that I chose to do. So again, to convert from kilojoules to joules, we got to multiply by 1,000, and we get the energy in joules per photon. So 1 photon has this energy associated with it. So now that we know the energy of a single photon, we can calculate the wavelength. And so again, we just rearrange wavelength and energy. So wavelength equals hc over E. Again, make sure you use parentheses. If you get some wild exponent like 10 to the negative 44 or 10 to the negative 50, most likely it wasn't entered into the calculator correctly. So we get lambda, it's 1.21 times 10 to the negative 7 meters. Again, we want it in nanometers. So we multiply it by 10 to the 9th, we get 121 nanometers. So again, some key things is make sure you divide by Avogadro's number to get the energy per photon, then convert it to joules. When you're using the equation, make sure you use parentheses. So the other part of what I asked you to watch in the first video covering atomic spectra dealt with the electronic transitions of a hydrogen atom. So in this description of the hydrogen atom, we refer to it as the Bohr model, where we have a nucleus, it's where the protons and neutrons are, and then we have these energy levels that surround the nucleus. And this goes from n equal 1 to n equal infinity. And so this is what the Bohr model of the hydrogen atom or hydrogen-like atoms species looks like. And so each one of these is an energy level. So the first energy level is n equal 1. That's called the ground state. And then after that it increases n equal 2 and so forth. And then n equal 3, n equal 4, and it continues as you go further from the nucleus. So the higher the n, which is the symbol for energy level, the further away your electron is from the nucleus. So let's say we have an electron on n equal 1. To go to the next energy level, to go up to a higher energy level, it has to absorb a photon of energy. So to go from n equal 1 to n equal 2, it has to absorb energy to go up. Now, if we had an electron on the 4th energy level, and it wants to relax back down to, say, the 2nd energy level, where here it releases a photon of energy. So to go down, you release energy. To go up, you absorb energy in the form of a photon. So here it asks which one of these electronic transitions is the absorption of a photon. So to know if it's an absorption of the photon, the first n is less than the final n that you're going to. So for example, n equal 2 to n equal 5, since 2 is less than 5, this one will require the absorption of a photon. N equals 7 to n equal 1, since the first n is larger than the second n, here we would release a photon, so we wouldn't absorb. N equals 6 to n equals 3, we would release a photon to go down. So anytime your initial n is larger than your final n, you're going to release a photon of energy. Anytime that the initial n is less than the final n, you're going to absorb a photon of energy. So n equal 1 to n equals 6, you would absorb a photon of energy. Now n equal 8 to n equal 2, since 2 is less than 8, you would release a photon of energy. And then likewise, n equal 5 to n equal 4, you would release a photon of energy. So the only two that would absorb photons is 2 to 5 and 1 to 6. Now the last problem deals with different classes of the hydrogen atom transition. And so there are 3 main classes of hydrogen transitions. We have the Lyman series, which occur in the UV region, and the final n is equal to 1. So whenever you're starting, doesn't matter, but the final n should always be 1. Now for the Balmer series, it's in the visible region, and the final n is 2. And then the Paschen series, IR region, final n is 3. Now the other n needs to be larger than 1, 2, or 3. So we're always going down to n equal 1 for Lyman series. We're always going down to n equal 2 for Balmer series. And we're always going down to n equal 3 for Paschen. So you're always going down energy levels, never going up. So all of these series involve the release of a photon. So that means we're always going from a high energy level to one of these three final energy states. And so now if we look at it, we have n equals 6 to n equal 1. 1 is our final state. 6 is higher than 1, so this would be the Lyman series. Next we have n equals 6 to n equal 2. 2 is our final state. 6 is greater than 2, so this is the Balmer series. Next we have n equal 4, but you see 1 is less than n equal 4, so this would not be a hydrogen atom transition of the Balmer, Lyman, or Paschen series, so we just put not applicable. N equals 7 to n equals 3. 7 is greater than 3. 3 means it's the Paschen, so this would be a Paschen transition. N equals 7 to n equals 2. 7 is greater than 2, and since it ends in 2, it's the Balmer series transition. Next we have n equals 2 to n equals 3, but notice 2 is less than 3, so this would not be a Balmer, Lyman, or Paschen series because you're absorbing a photon, not removing a photon. Next we have n equals 3 to n equals 1. 1 is less than 3, so since it ends in 1, it's a Lyman series transition. And then lastly, n equals 3 to n equals 8. Well, 8 is neither of these three series, and secondly, 3 is less than 8, so this would be an absorption of a photon, not applicable. So the final state tells you which type of series it is and which region of the electromagnetic spectrum it occurs in. The initial state should always be larger than one of these three final states.